Okay. Yeah. So there are different types of chemical reactions. So of course a chemical reaction is one in which new substances are formed. We just talked about that a long time ago. So there's exchange reactions where the cation and anion change partners. There's acid-base reactions, and we've talked about those. There's precipitation reactions. There's combustion reactions. So there's this type of reaction called an oxidation-reduction reaction. And all it means, and I haven't really done this before, but I kind of want to start to kind of get you thinking. All it means is that something is oxidized and something is reduced. Thank you. So I think, you know how we've been doing kind of the A, B, like that's a compound, plus C, D, you know, goes to form. And I'm going to go ahead and, let's see, what do I want? I'll do an exchange reaction. So I'll go ahead and do AD plus CB. I know that's kind of strange, but. So an oxidation-reduction reaction means that something is oxidized and something is reduced. So I'm just going to circle my A, or not circle, but I'm going to put a thing over my A. I'm going to go over here. So for instance, that is, I'm going to say reduced. I'm just going to floor kicks do that. And then I'm going to pick on D. I'm just making this up as I go. I'm going to pick on D, so I'm going to start here. I'm going to go from the reactant side to the product side for that atom. I guess it's an atom, atom D, and I'm going to say oxidized. Okay, so that's what we're talking about. Something is reduced and something is oxidized. Just for kicks, I picked on A to be reduced, and I picked on D to be oxidized, just for kicks. Okay, so that's a redox reaction. By the way, oxidation, reduction reaction, they're usually called redox. Get it? Reduction, oxidation, redox reaction. Same thing. Okay. So one of the things we need to do is to kind of hone in order to identify, let's put it this way, and you guys are going to have homework that's going to be due on Friday. In order to identify, for instance, atom A is being reduced and atom D is being oxidized, we need to assign oxidation numbers to all the atoms. Okay? And so we need to talk about how do you come up with oxidation numbers for everything. So that's what we're going to talk about. I'm going to show you kind of a more involved way of coming up with oxidation numbers for all the atoms, and then I'm going to show you kind of more, give you some more rules that are real easy. Okay, so just bear with me. But oxidation numbers are for a given atom, basically what is its charge or parent charge at what we call the ionic limit. Now this is kind of strange. So the ionic limit is not a real situation. Basically, for instance, if we pick on AB, I could put a triple bond there, A triple bond B, okay, two atoms joined together, let no man put us under, go ahead and make complete octet, right? We are going to come up with oxidation, we are going to come up with an oxidation number for A and for B as if that wasn't a covalent bond, it's ionic. We'll talk about that, okay? An ionic limit. It's not real, but, okay? So what that ionic limit will tell us is kind of how the electrons are distributed in kind of a non-real situation. So just bear with me. It's easier to show you than it is to describe it. So the ionic limit, okay, like I said, the ionic limit is going to assume, and we're going to do one example with a molecule. We're going to assume, for instance, that this triple bond here, that those electrons are not being shared, okay, that actually electrons, those 6 electrons are going to be transferred, okay? It's ionic. So just bear with me. So in order to do this this is the harder of the two ways. In order for us to kind of think through this, we need to, do you see my little silver pen? We need to remember, thank you. We need to remember the trend in electronegativity. Electronegativity is that chi thing. Electronegativity, I know. So we said that for the group A elements, electronegativity is that, and electronegativity increases across for the same period, and electronegativity increases from the bottom up in the same group. Okay? That's the chi. So that's actually going to be a player. So in order to come up with these oxidation numbers, we need to assess the situation as an atom is bonded to another atom. And what we're going to do is the atom that's greater electronegative, we're going to give it the lines, we're going to give it all of the electrons. So just playing devil's advocate here, let's just say that B was more electronegative. Let's just say it's more electronegative in this case. Actually, it's going to go ahead and get all 6 of these.
Is that the Pauli numbers?
No,
No. Okay.
don't think so. But we'll kind of revisit that. So at the limit here in a minute, we're going to see that actually B at the limit, at ionic limit, in this kind of fictitious thing that I've kind of come up with on the fly, basically B is going to look like this. It's going to actually have 6 electrons at the ionic limit. Yep, it's kind of weird. And at the ionic limit, guess what? A will be just that. Okay, that's kind of what we're talking about. Okay. So if you're good with that, those are electrons at the ionic limit, and that's in the situation we're assessing. So in order to come up with the oxidation number for each one of these atoms, we need to do a little subtraction problem. So what we do is we look at the periodic table and come up with the number of valence electrons. Now this is where I can't apply this to this. We come up with the number of valence electrons for that element. And if you want to, up at the top of this, valence electrons, if you want to put the group number, you can. So it's the group number of 4 main group elements. Valence electrons you get from the periodic table. And then from that, we subtract the electrons at the ionic limit. And that's where you get from assessing the structure, the context. Okay? So let's do an example. Again, this is coming up with oxidation numbers for atoms this way is harder than the other way, but they're both consistent with each other. And you need to know both of them. So we're going to pick on carbonyl dichloride. So we have a central carbon atom, singly bonded to 2 chlorines and doubly bonded to an oxygen. And for each of these 4 atoms, we're going to assign oxidation numbers. Okay? So we need to pick it apart, and we need to come up for each atom, we need to come up with the number of electrons at the ionic limit first. So I think I pick on the oxygen first. Now, if we look at a periodic table, we're going to pick on the oxygen, and it's doubly bonded to a carbon. Oxygen and carbon, which one's more electronegative? Oxygen is more electronegative. So it's going to get those 4 electrons. So this is what the oxygen looks like. Yep, makes sense? Then I think we're going to pick on each of the chlorines, and they're actually symmetrical. So they're singly bonded to a carbon. Which one's more electronegative, carbon or chlorine? It's a tough one, but chlorine. Chlorine is more electronegative, exactly. So those 2 electrons that make up that single bond are going to go to each of the chlorines. So they both look like this. That make sense? So those are the electrons at the ionic limit. Now what did that leave carbon? Nothing. It's bare. Poor thing. Okay? So that's actually, when we do subtraction, that's the second number. So we're going to have what? Go ahead and do the math. For carbon, picking on carbon first. This 4 came from the 4A, the valence electrons around a carbon atom. And that 0 came from the number of electrons at the ionic limit. So 4 minus 0 is 4. So actually, we could, and if you want to, you can. It's the way my builds go, it's going to be erased here in a minute. But we would say the oxidation number is, I usually go plus 4. That's it. We're going to do it for, what are we going to do next? Oxygen. So it's 6A, so that's the number of valence electrons. In this context or situation, we came up with 8 electrons at the ionic limit. So 6 minus 8 is minus 2. So we would put an oxidation number for the oxygen as minus 2. Now the chlorines, they are 7A. So we'll put 7 minus the number of electrons at the ionic limit, which is 8. So 7 minus 8 is minus 1. Now one of the rules, and it's gosh, I think I printed them off for me to look at, but one of the rules for assigning oxidation numbers, so we said that was what, plus 4, we said that that was what, minus 2, and these are both minus 1, minus 1. One of the rules, honestly, is that if you have a neutral molecule like this, all the oxidation numbers need to add up to be equal to 0. And that's totally what we got going on there. It's wonderful. And there's an easier way, kind of, I guess, and I'm going to show you, but that's what we're talking about.
That's just for a neutral, you said?
Yep, just for a neutral molecule. So those are oxidation numbers. And again, to kind of put this where it needs to be for today and tomorrow's lab, when we talk about redox reactions, like I've kind of tried to draw up here, redox reactions, what's going to happen is you're going to see a change in oxidation numbers. Something's going to be oxidized and something's going to be reduced. Now I need to talk about what those two terms mean. But those oxidation numbers are going to change on either side of the reaction arrow. Okay, so this is a little easier, and they, again, are consistent with what we talked about just a minute ago. And this is the one that I printed out for me. So I got like 5 slides. I know.
Your bag.
What's that?
Your bag.
My bag. I use this bag periodically. Our daughter got that for me. Okay, so the first rule is that if you have something in your chemical reaction and it's in its uncombined elemental form, then its oxidation number is 0. It's awesome. Makes life easy. Okay. If you happen to have an ion and it's just one atom, monoatomic ion, okay, then the charge on it is its oxidation number. So for instance, sodium, yes, it's like sodium's +1, its oxidation number is +1. Oxygen, if it's an ion, is oxygen -2. As an ion, its oxidation number is -2. Okay. Okay. So if you happen to have an ion and it's polyatomic ion, and it's only one type, and the example I have, I'm going to show you here in a minute, is the triiodide, which we don't do a lot with. But triiodide is I3, and it's got a -1 charge. It's got a -1 charge for those 3 ions, those three atoms. And so what this says is that what you do, if I was going to draw this, okay, oops, there's my polyatomic, okay, like that, then actually each one of them is this charge divided by, there's 3 of them. So this is a -1/3, oops, -1/3, -1/3. See how that goes? What are you laughing at?
Your 2 through 4-ish thing.
Like what?
Your first 3, it looks like a 2 and then a 4 and
Oh,
a 3.
okay.
It's fine.
This one?
Yeah, it's fine.
Because it started out as a 3. Or 2. It started out as 2. Okay, well, you get the idea. Then we have a few elements, and this will help us when we, in a minute, when we kind of turn loose a little bit, looking at, for instance, not in context of it reacting with anything, but if we just look at the formula of a compound, we can hang our hats, remember that phrase? We can hang our hats on hydrogen generally being a +1. Hang our hats generally on hydrogen being a +1. Unless hydrogen is combined with a metal in a metal hydride, and then it's a -1, but it's usually +1. Hydrogen's usually a +1. Oxygen's usually a -2.
Sorry,
Okay.
what?
What's that?
Oxygen's usually a +2,
-2.
-2.
Hydrogen's a +1 usually, and oxygen's a -2. So when we're having to deduce something whose oxidation number, and oxidation number, sometimes we call it oxidation state, varies, okay? Then we can deduce what the oxidation state is by picking on these things that we know. Okay? But this says like H2O2, hydrogen peroxide, that's not going to be the case with regard to the oxygens there are each a -1. But we don't have this situation very much.
So if it's O2 by itself, is still -1?
If it's O2, like molecular oxygen by itself, that goes back to rule number 1.
Oh.
So it's 0 actually. Yeah. Yeah, O2 by itself, each oxygen is 0. If oxygen is in a compound like H2SO4, O4, those 4 oxygens each bring a -2 oxidation number.
Sorry, so what's the difference between that triiodide and in its elemental form, O2?
Okay, well, actually, we can kind of compare that. Okay, O2, there's no charge. Okay, so if you want to divide no charge by 0 by 2, you're going to get, yeah. That makes sense, it's kind of the same deal.
No, but that's okay.
Okay, to me it's similar, yeah, because in each case, we're dividing this number by the number that there are, this
Yeah.
number by the number that there are,
Yeah.
yeah.
Okay.
So it's just 0 divided by anything, 0.
Well, yeah, yeah.
Don't overthink it, Marie.
Well, that's why, we can, go ahead.
Oh, okay. This was the one that we applied to the dicarbonyl, dichloride, the thing that we looked at, the molecule we looked at. We said that if it's neutral like it was, all of the oxidation numbers need to add up to be equal to 0. And we're going to use that as a tool to kind of deducing what the oxidation numbers of atoms are here in a minute. If it's neutral. Now, if it is an ion, a polyatomic ion, like NH4+, okay, NH4+, ammonium. Let's go ahead and do that one right quick. So hydrogens are +1, right? So I'm going to put a +1 for each of those 4 hydrogens. And I don't know how I want to show you this, but do you buy this? If I take 4 hydrogens times +1 plus question mark for the nitrogen, it's got to be equal to +1. Does that make sense? It's like a little Sudoku game, kind of.
Okay.
Yeah. So what does that question mark need to be? Not -4.
I mean,
1/4.
oh,
Oh, wait, no, plus, so it'll be -3.
-5, what? Oh, 3, yeah.
Do you guys both agree? I agree. Question mark is equal to -3. Yes, exactly. And nitrogen is one of the, actually, we think of it as being, group 5A. If it's going to form an ion, it'll pick up 3 electrons and be a -3. But nitrogen is not always oxidation state -3. In that case, it is. Yeah, exactly. That's it. You look like you're on board with this. No? Yeah. You will be.
Yeah.
Okay. So let's do some. Okay, this H2 is kind of like the O2 over there. So do you guys have the answers for these already?
No.
Okay, so what is the oxidation number for each of the hydrogen atoms?
1. Or-
No, it's not,
Why is it 0?
because it's in its element.
wait,
Yep.
Right now.
Rule number 1. Rule number 1, exactly. Yep. Each of the hydrogen atoms' oxidation state is 0. How about magnesium? 0. How about the 4 phosphorus atoms making up P4?
0.
0. Yep, I'm liking it. How about the sodium in the sodium plus 1 cation? What'd you say?
1.
Plus 1, exactly. It's just the charge. That's rule number 2. Yep, rule number 2. Awesome. Okay, what about the nitride ion?
So that's gonna be
-3 is its oxidation number. Perfect. What about the mercury 1 polyatomic cation? Everybody hates that one. I hate it too. What about each one of those mercury atoms? They are a +1, exactly. Does that make sense? They are a +1 because
You take the oxidation number divided by the number of.
you take the charge
Yeah,
divided by the number there are. Yep, yep, exactly. That's kind of like we were doing over here.
So it's just 2 over 2.
So we take the what do we say? Yeah, the charge divided by the number that there are. Yep. So +1, +1. Perfect. Yep. How about, and then we already did this one. So what did we say the oxidation number is?
1.
Yeah, for each of those iodine things, each one of those I's, they're
it's
-1/3.
Negative, sorry.
Yep, exactly. So oxidation numbers don't even have to be whole integers. Is that not awesome or what? Very good. I think we've got a few more. Okay. Now, in the water molecule, actually, to me, they follow rules number 4 and 5. So what's the oxidation number for hydrogen?
Because it's not in its elemental form?
Right. It's not in its uncombined. It's not as uncombined, which means it's not combined with anything else. In this case, we have oxygen combined with 2 hydrogens. So hydrogen is a.
0?
The whole thing is neutral,
Oh,
but which are the hydrogen atoms?
hydrogen.
+1,
Yep, +1 each, and then oxygen
-2.
-2. Exactly. The hydrogen. So rule number 4 here says, and you aren't. I'm not going to throw.
Well, I keep trying to add them together, like the whole thing, so each one, okay.
Yeah, each one. Each added together, they're 0, but each one individually, the hydrogens are each +1, oxygen -2, added together 0. Okay, so to me, the next one, let's kind of do it together, kind of like we did the ammonium. We don't know sulfur, so I'm going to go ahead and put a question mark over sulfur. So what's hydrogens? They're each +1, perfect. And oxygens are each -2. And then if you think it's like a little math problem, we have 2 times +1, oops, plus question mark, plus, let's see, 4 times -2 is neutral. That's kind of how I think of it.
So +6.
Is it +6? So we got a -8 plus 2 -6. I got +6. Is that what you said? Me too. Does that make sense? Yep.
Why don't we know S, because?
You don't, because it's not here.
Use the rules IH.
You don't know. Most atoms can have multiple oxidation states, and they participate in redox reactions. Hydrogen is usually +1, oxygen's usually -2, and they will be for us on the test and everything in our examples. Everything else, the bets are off.
Okay, so this particular example just happens to line up with
Right.
its group number, but it's not always.
Nope.
Okay.
No, and actually, this is a good example. It lines up with this group number, but sulfur, remember we said it's a 6A, so it usually pick up 2 electrons and, form a -2 anion. So anyway, it's not, from other stuff we talked about, yeah. So its oxidation state in sulfuric acid, sulfur is a +6. Well, it won't always be, exactly. And yeah, we already picked on ammonia. Okay, so we said that each of the hydrogens are +1, right? And we said question mark for the nitrogen. And when we did the math here, you told me nitrogen's -3. Okay, and you were right. Okay, so let's do would that be chlorite? Yep, together. So the only thing, you can't hang your hat on the chlorine, so I'm going to put a question mark over the Cl. But I'm going to go ahead and put -2 over for the oxidation for each of those 2 oxygen atoms. So I'm going to take 2 times -2 plus question mark is equal to, I have to say it's equal to -1. Does that make sense? Okay, because that's the charge on the polyatomic anion. So what's our question mark there?
+3.
I agree. Does that make sense? +3. Yeah, so the chlorine atom in that context, in that polyatomic ion, is a +3. That's totally right. They're kind of fun, actually. And they're even more fun when you see them change on either side of the reaction arrow in a redox reaction. Any questions, or is it still not yet? Okay. So, but like what I tried to say is whether you apply what we did a minute ago with the charge at the ionic limit, or whether you apply this, you'll come up with the same thing. But you need to be able to do both, as far as I can tell. All right. So now here's where I'm going to actually go back to our mythical AB plus CD goes to form AD plus CB. I'm going to kind of superimpose on that some terms. Okay. So oxidation means that in this case, when I said D is oxidized, what you're going to do on either side of the reaction arrow is see the oxidation number go up. That is so cool. I guess it's just me and it's the end of the semester. But, so for instance, it looks like this. We will, when we get going, we will assign little oxidation numbers for all of these. We can do them for C and B, but they're kind of duds, actually. C and B, there's no change. Okay? In this case, if D is oxidized, you're going to see, I'll put it up here, you're going to see oxidation number increase for D. I'm going to say 4D. Okay? And then over here, reduced, I'm going to say that oxidation number for A increases. Okay? So we kind of have some semantics. Tomorrow's lab, we are going to be tracking electrons. And does this make sense that, like for instance, if you had an oxidation number of +2, and let's just say it was reduced to 0, the way that works is actually it's reduced and it actually takes in electrons. Okay, so the thing that's actually reduced, okay, how do I have it here? Gains electrons. Gains electrons. It's reduced, it gains electrons. Electrons are negative, and they actually kind of dampen down your oxidation number. Okay, things that are oxidized, okay, they actually give up electrons. Give up electrons. And as they give up electrons, they become more positive. Oxidation number.
Wouldn't the oxidation number for A decrease? Or do they both increase?
You always have to have one atom that is being reduced and one atom that's being oxidized. And
Right.
I just...
Yeah.
Right, but you have D is increasing, so wouldn't A be
Oh,
decreasing?
thank you.
Yeah, that's
Yes. Thank you, yes, perfect. Yep, that's what reduction is. Thank you. Decreases. Better. Okay. Good. So now a little bit of semantics. Of course, we've talked about reactants and products, okay? A reactant is actually the whole thing, not just the atom, the whole thing. So the reactant would be, for instance, the whole AB species here, okay? This is the reactant that contains the atom that's being reduced, okay? It's losing, oh, sorry, I got my things mixed up. This over here. D is the atom that's being oxidized. So CD is the reactant that's has the atom that's being reduced, oxidized, excuse me. Okay. So put another way, I said, and I kind of, I'm out of sync a little bit, but if we pick on oxidation first, okay, this reactant, the whole reactant, not just atom D, but the whole reactant we say is undergoing reduction. I'll put it that way. Undergoing, oh, darn it, oxidation, thank you. Next time I do this, I'm going to make A my thing that's being oxidized. Undergoing oxidation, thank you. We say the whole reactant is doing that even though it's the one atom. Okay? We say the whole compound BC is undergoing what, reduction? Good. Like I said, this is my first semester to take a stab at this. Just kind of building. Okay, but wait, there's more. Okay? So if you think of like agent of change, okay, an agent of change. So an oxidizing agent is making oxidation occur, okay? So an oxidizing agent actually is generally the thing that's undergoing reduction. So undergoing reduction, I'm going to say oxidizing agent. Oops. Now, don't blame me. I don't know why we have all these terms. And I'm kind of thinking it's been so long ago that I applied to grad school in the area of chemistry. But I swear that they had some of these terms on there. You're like, really? So yes, they are out there. Okay. And then with regard to the thing that's undergoing oxidation actually is the reducing agent. So we said CD was undergoing oxidation. The reactant was undergoing oxidation. This is actually the reducing agent. Secret agent man. That's what I mean. Okay. So again, don't blame me. It gets really confusing when you have the same within one reactant, it has an atom that's undergoing oxidation and an atom that's undergoing reduction. It's like, oh, well, there you go then. So let's go with something a little easier than that. So here's where we're going to do some examples. I was getting ready for today's lab, and I'm like, oh, okay, combustion. Yeah, that's like where you burn stuff, right? Combustion, we talked about combustion analysis, where you have this kind of cool little furnace, and we talked about burning hydrocarbons, and we ended up with carbon dioxide and water. But combustion doesn't have to be just burning things. It just means that you're combining reactants or a reactant with oxygen, and most of your products have oxygen in them. So the example we're going to talk about is rust. Okay? So what is rust? And actually, here's where I need to tell you, none of my movies are working. I have a call into our person who does IT here, and we're going to hopefully get some videos working for Friday, but not so far. So these aren't going to work. So we're going to talk about oxidation.
Sorry,
Yes.
Did you say rust is combustion?
Mm-hmm.
Okay.
Yeah. Yep. Rust is combustion. Yeah. That's kind of weird. Okay, it's combustion because you're combining iron with oxygen to form iron oxide. Okay. So before we do this, if you don't mind, and I'm only going to do it on this slide, and you'll have to refer to it in the next slide when we ask questions too. Let's just go across from left to right, and let's assign oxidation numbers. So this is what I would suggest you do. So iron, what's the oxidation number for Fe there? It is 0. What about the oxidation number for each of those 2 oxygen atoms in the O2? So what's the oxidation number?
No. What?
Uncombined. Why is it 0?
Because it's not combined, it's not.
Because it's
Yep. Very good. Okay, so now let's go, actually over here we have to deduce the iron, because what is the oxygen there? They are both, yeah, all 3 of those are -2. Perfect. So we have a -2 times 3, that collectively gives you -6. It needs to be balanced by your Fe, and we've got 2 of those, so how much are each one of those?
-3, they're +3.
They are +3. Does that make sense?
each one.
Each one is +3. Yes, perfect. So if we were going to go ahead and kind of like I have over there, kind of pair them up, can you see where the Fe is going from 0 to a +3? So is that increasing or decreasing oxidation number?
Decreasing.
It is increasing. Increasing oxidation number.
Oh, increasing oxidation.
Decreases in your electron.
Yeah.
Yep. So then kind of all of this stuff falls into place with regard to the Fe, excuse me, yeah, with regard to the Fe. Okay, and let's go ahead and draw an arrow from the O2. Well, draw an arrow from the oxygen on the reactant side to the oxygen on the product side. So it's going from a 0 to a -2. So what do you think? Is its oxidation number increasing or decreasing? Decreasing, yep. Decreasing oxidation number. So that oxygen must be being reduced, and we kind of have all these things associated with that. So for the first question, which atom is undergoing an increase in oxidation number? What's the answer there?
What? Which atom is undergoing an increase in oxidation?
Which atom, yeah. So
Atom. Increase.
you said, yeah. Yep, you both said iron, yep. Perfect. So which atom is undergoing a decrease in oxidation number? The oxygen. Perfect. But I really think that when you do these for your homework or on a test, I would just go across from left to right assigning oxidation numbers. There's one exception. I'll kind of show you what that is. Okay. So now be careful, it does not atom. So which reactant? So reactant's the whole thing. Which reactant is being oxidized? The 4Fe, or just the Fe solid. Fe solid, very good. But I like that you wanted to make sure that you don't need the stoichiometric coefficient. Which reactant is being reduced?
O2.
The O2 at G. Very good. And then this is for the mind boggler. So with regard to being an agent, which reactant is the oxidizing agent?
O2.
It is O2. Very good. O2 gas. Which reactant is with regard to being an agent, a reducing agent?
Iron.
Yep, Fe solid. The one that's oxidized. Perfect.
Is this a mahjong thing?
Maybe. Yeah, that tile game. Yeah, I think it might be.
Matching really helps me.
Okay. If this is a mahjong game, there'll be a little bit of, you need paper and pencil, because I need paper and pencil to think them through. I have to put the little pluses and the minuses, and then, yeah. So, okay. So we're going to look at zinc. Let's do it on the next slide, okay? But this actually, how do I say this? I like this. This is kind of called a plating sort of situation. Notice that we start out with solid zinc and we end up with solid copper. Okay? And it is a redox reaction. Okay, so it kind of still images look like this, where the first solution is the stick thing is the zinc, and the blue, pretty blue on the reactant side is the copper 2 sulfate. And then when zinc is submitted to copper 2 sulfate, electrons are transferred. We'll be talking more about that. Or not transferred, but electrons, yeah. So the oxidation state of the copper and the zinc, one's reduced, one's oxidized, and you end up with this solid copper. So at the molecular level, remember I told you the shtick was zinc, okay, it's solid zinc, so there is a redox reaction happening at the surface with the blue-colored liquid, specifically the copper 2 in the blue-colored liquid. So let's do what we did before from left to right. What is the oxidation number for zinc? It is 0. Perfect. Let's see. In copper, now here's where I'm hoping we're kind of all on the same page. This actually is a Chem 1 sort of thing. Copper 2 sulfate should scream to you ionic compound. No? The sulfate ion, what's the charge for sulfate ion? -2, very good. If that's -2, then in this case for this salt, yeah, it's a +2. You have the oxidation state for copper right there. Does that make sense? Now, here's a trick I'm going to show you. So do you see where we have sulfate over here and sulfate over there? Now, oxygen's going to be -2, and we know that sulfur can have multiple oxidation states. But if it's sulfur and sulfate over here and sulfur and sulfate over there, do you see where it's not changing its oxidation state? I'm not even going to mess with it. So let's keep going. What about the zinc here?
+2.
It is a +2. Why?
Because the sulfate is still negative.
Yep, exactly. And plus zinc is one of those transition elements we know is always a +2. Zinc and cadmium are +2 and silver's +1. Perfect. What about the copper over here? It is a 0. So in a redox reaction, we're always looking for something to increase its oxidation number, to be oxidized, and something to reduce its oxidation number, to be reduced. So let's pick on the zinc. Zinc is going from a 0 to a +2, so what do you think? It's being oxidized, yep. And let's look at the sulfur. Sulfur is going from a sulfur. Let's look at the copper, Cu. Copper is going from a +2 to 0. So what's going on there? Reduction or reduced. Very good. Perfect. So when it says not atom, but which reactant? So I'm reactant. Which reactant is being oxidized?
To use CuSO4 is just Cu. Or oxidized.
Zinc solid. I'm liking it. Zinc solid. You got it. And then which reactant is being reduced?
Copper 2 sulfate.
Yep, copper 2 sulfate. CuSO4AQ. Oh, wow. I think you'd be good writing CuSO4AQ. Which reactant, with regard to being an agent, then, is the oxidizing reagent? Yep, the copper +2 or the copper 2 sulfate. I take either one there. And then which reactant is, with regard to being agent, the reducing agent? Yep, zinc. You got it. And hopefully, this is one of the things we're going to talk about a little bit tomorrow and even more on Friday, is the whole battery thing and redox reactions. Most batteries, or a lot of batteries, use redox reactions to produce electricity. So let's go from left to right here. Oops. Saying what everything is. What about the zinc solid? It is 0. Awesome. Okay, what about the oxygen and MnO2? -2, I'm liking it. So if that's a -2, there's 2 of them. Collectively, they bring a -4. What's the Mn there? It is a, yep, it is a +4. Perfect. So remember, we just focus on making that add up to be equal to 0. All right, how about the ZNO? So we're going to go with oxygen -2. So what's the zinc? +2. Mn2O3. Each of the oxygens a -2, so collectively they bring a -6. There's 2 Mns. They need to make the whole Mn2O3 neutral. So how much is each one of the Mns? +3. I'm liking it.
Oh,
Yep. So we could go ahead and kind of pair up. Something's got to be oxidized. Looks like the zinc maybe being oxidized. And the Mn must be reduced. It's going from a +4 to a +3. I call that reduced. I'm liking it.
okay, you're just thinking about each one,
Each atom, yep.
each atom. So it's reduced just basically 1.
Right.
4 to 3, okay.
Mm-hmm. Yep. You got it. Okay. So those ones I skipped over, actually you on your own could go through them, and what you would find on either side of the reaction arrow is something being oxidized and something being reduced. So let's take a look at the homework. It's weird, it's back to chapter 5. You're like, really? Yay! Nothing like going from 19 to 5. So it looks like this. Cool. Okay. So, excuse me, it's kind of like what we've been doing. Now, A, B, C, and D, they're not all redox reactions, and that's actually what you're tasked with. You're supposed to, like for instance, I did A for you here. Okay, when I did A, I couldn't find any atoms that were being oxidized and reduced. Notice the magnesium went from +2 to +2, carbon went from +4 to +4, oxygen went from -2 to -2, hydrogen went from +1 to +1. You're like, dude, there's nothing going on here. There's no redox chemistry going on. So in other words, for your homework, you don't have to do A if you don't want to. Just say Mrs. Snipes did it in class. It's not a redox reaction. So you can do B, C, and D. For the next question, it looks like this. And I've gone ahead and done A for you. Again, you can say Mrs. Snipes did it in class if you want to, but go ahead and do B for credit. So basically, I evaluated A for you. And notice when I did it, I see the irons going from a +3 to a +2. The manganese, yeah, I get my magnesium and manganese mixed up. The manganese is going from a +7 to a +2. So I got them both being reduced. And you're like, dude, that can't happen. Okay, so I've done A for you.
So is that at abbreviated form acceptable? We follow that abbreviated
Yes,
form?
you can follow that abbreviated form, so you just need to do B. Yep. And I think you're going to find it doesn't make sense either, okay, when you assign oxidation numbers. And then the last one looks like this. What are the oxidation, and it's kind of like what we did in sample problems. So the whole agents thing kind of gets me frustrated because the oxidizing reagent is the reagent that's being reduced. You guys did it just great in lecture. So you'll have to, okay. So again, assign oxidation numbers. It's fun. I tell you, you're going to want to just do a whole bunch of these. So that will get you in good shape for tomorrow's, tomorrow. So I'll have to figure out, I don't know, we'll have to see how much energy I have. We might just I have a really cramped, abbreviated form of part 6 that we might go with. So we'll see. Okay, so we'll see you for lab.
There's another slide
one of the
between
rooms. What's that?
Half
There's a
reaction.
slide after the.
Oh, okay, thanks. So this is kind of an introduction to tomorrow. We are going to be balancing equations, because you know how we do it by inspection, come up with the stoichiometric coefficients to balance the equation. Well, we're going to do it by tracking the redox reaction, the flow of electrons. We'll kind of show you how that works tomorrow.
So
So
I can't use my handy dandy algebraic.
no,
Yeah, but I like
because
that.
we're going to be introducing hydrogens, and I don't think that it's going to work. I don't think. But you'll get lab credit just by